Hello guys, so today I will start a series on simple linear regression and I will do in small bits and pieces but I will complete the entire theory. So as we talk about simple linear regression, the first part consists of model and algorithm of the simple linear regression. Okay, so let's discuss this in the first part of the video. So where does simple linear regression arise from? People saw graphs like this saw some scatter plots, and this and saw like they sort of thought that okay, maybe a good line fit is possible, right? So maybe this data as to x and y's are sort of linearly related. They assume that, but they have some errors over here, so they're sort of modeling it. So I'm just telling in a very simplistic view. So you can use this video for your revision purposes. So therefore, the model sort of came in this format. So they have this. They understood that there may be some sort of relationship between y and x, right? So they did the following. What they did is that they assumed. So first of all, there is a data. The data is over there, and which is of the form xi comma yi, right? And they have then the corresponding model. Initially they thought that yi must be of some, actually yi must be some function of xi plus some corresponding epsilon I, the errors, right? So if you consider this corresponding format, then you will get the following. So you will get that, and if you assume that f is equal to beta naught plus beta 1 xi, what will you get? That is fx is equal to beta naught plus beta 1 x. That is a simple linear format. That's why the name is simple linear regression. Then what you will get? You will get that yi is equal to beta naught plus beta 1 xi plus epsilon. That is exactly simple linear regression because you assume that relationship in y and x is sort of simple linear. Okay, there is multiple linear regression too, where there are multiple terms. So this is the model, basic model based upon which we have like developed the whole theory. Now, what is the next part? Since it's statistics and since we live upon errors, statisticians live on errors, they eat on errors. So it's not also natural. So if you collect the data, there is sort of natural tendency to have an error, right? That's a human law. That's a natural law. So therefore, what we assume is that this epsilon I is random. Okay, it is an error, and it's a random error. So what we assume, it's like it follows some distribution P with mean 0 and variance sigma square. Okay, so this is the following assumption. So this assumption that it's a mean 0 is sort of telling that the error sum will be sort of like the basic part. That means it tells that expectation of y given x will be actually beta naught plus beta 1 x. So essentially the average value will be that. Okay, so that is natural, right? The errors will be sum will be 0. And also this condition sigma square may not be true always. So it's called homoscedasticity, that the errors are similarly like distributed in terms of variance. The variance is same. And what's next? Next part is that the next part that is there is that EIs must be normal. Sorry, not more normal, but it's an assumption part of it. But rather EIs must be independent of each other. Right? Normal is an assumption. It's most probably not true in every case. Okay, but it's a model assumption because you will see that in case of normal least square method and the minimizing the maximum likelihood estimate will be the least square estimate and maximum likelihood estimate will match. Okay, that's why normal are really beautiful. Normal is really beautiful. Normal distributions are really beautiful. So essentially it's normal 0 comma sigma square, but normal can be dropped off for the least square part. Okay, you don't need the normal for the least square part, but it's an extra assumption. So this is the steps that we need for the entire like simple linear regression. Very basic and beautiful steps. Okay, so you must remember this simple linear regression model. The expectation is this. that is the mean of the errors is 0, and it's homoscedastic, and they're independent. Okay, this is very important. They're independent. The errors must not be correlated with one another. Okay, they must be independent. Okay, so this is the basic model. So now how will we analyze this model? How will we actually get to know about this model, like more about from the data? That's the algorithm. What that's actually the machine learning algorithm. That's actually the statistical learning algorithm. Okay. So how to do it? So there is a specific way of it. Okay, and we will follow the same way. So first we get the data. As you know, we get the data xi comma yi. We first get the data xi comma yi. What we do next? We have this model then. What is the model here? Y is equal to fx plus epsilon. Okay, where f here is beta naught plus beta 1 x. Okay, here is xi comma yi. Here is the f. We are assuming it. That is yi equal to beta naught plus beta 1 xi plus epsilon I. Okay, this is a beautiful idea. And then what comes up next? Next thing actually comes up is the, so we have defined the model, and we also defined the model, essentially the model over here. Epsilon follows something 0 comma sigma square, and they're independent, and all these things. These are the model part. Okay, so this is the model part. And then comes up that, okay, you have fitted this model good, but how to find the model? Like, we don't know this beta naught and beta 1, right? We have to, for different data it will be different, right? So for this kind of data, the beta naught will be different, beta 1, beta naught. For this kind of data cloud, the beta naught and beta 1 will be different. So how do we actually find it, right? How do we find the actual line? So that is by the loss function. We need something called the loss function. Okay, and that is the idea of least square. That's an algorithm. Okay, the least square algorithm tells that we define the loss by the square error loss. The loss is actually L. Okay, before that I must tell you one thing, that this f has two parameters. So it's actually f theta of x. Okay, the theta is the two parameters. It's actually, I'm telling the scenario of parametric models. For non-parametric models, the infinite amount of parameters, but here a function is denoted, it has a bijection with the two parameters. Okay, the parameters are, the corresponding parameters are theta equal to beta naught and beta 1. Okay, for this simple linear regression. So remember, it's very important. Okay, these parameters are very important because we will essentially mapping the functions with the parameters. So essentially, if we can sort of find the beta 1s and beta naughts and beta 1s, we'll essentially find the function, okay, which we are trying to find, the perfect function for the xy data cloud. So what we do, we have the least square. The least square is actually L of theta. So it's a loss function. In this case, it's a least square where it's summation of yi, the datas, I from 1 to n, let's say the n datas, yi minus this f theta of xi whole. It's sort of the all the sum of the squares, okay, sum of the errors, sum of the squares of the errors, okay, that we have observed. And this is the expected. So for different theta and theta naughts, we have L theta, right? So if we put in theta as 1, 2, we get a different L loss. If we put different L thetas, will so essentially L, this loss function, because we know this yi and xi, okay. So essentially we are trying to sort of model the error sum of squares, sum of the error squares. So residual sum of squares, okay. So we are sort of minimizing this sum, okay. Why? Because for the, so essentially this loss is a function of the parameters, okay. So for what theta you will choose? This is the theta and this is the L, right? You will choose the theta for the minimum loss, right? We want to find the function where it's a minimum. You don't, for this data cloud, you don't want to select that like this, right? Because the loss, you can understand, like loss is like not good. It's much more, right? So we want to minimize the loss. Therefore, the next step is that we want to minimize the loss. If you want to minimize the loss, what we get is the theta hat. After minimizing loss, in this case, why it's taken square? Because the square has a minimum, unique minimum, okay? It's a convex function. That's why it's a unique minimum. So therefore, this is very important. That's why it's often told that we take squares because of the calculus part. This is the reason, the calculus part. We have to minimize the thing. So minimizing the thing is very easier for this easier stuff. That's why we don't take modular stuff. Okay? The algorithm is very hard. For different loss function, we have something called stochastic gradient method, not stochastic, but gradient descent method. Sorry. And for there, what we do is that we have to minimize. Say there's an algorithm to minimize the loss. Okay, that's topic for a different video. Here we minimize the loss by minimizing the least square method. Okay, and what we get out of this least square, we get the following: arg of mean of theta of L theta, for which we get the minimum loss function. That's it. So this is the basic model and the algorithm of the simple linear regression. The second part of the video consists of asking and seeing that turns out of loss functions, or minimizing loss function, and we get something called normal equations, and from there we will find this estimates. Okay, that's the part of the next video. See you guys in the next video. Stay tuned, stay blessed.